So yes, now it has given me the reproduction points and the reproduction errors what I have. So we were expecting to be as minimum as possible. So let us just explore a few more images and the reproducted points. So okay, so most of them are like is accepted. So I have like currently my reproduction errors is 0.6, and still it's recommending me like there is uh, the blue line to. So let us just drag this and like get it less than 0.5 or let's say less than 0.4. So we'll have all the images that has reproduction errors, which is less than 0.4. And it's going to select highlight all the images that have the higher reproduction errors. So what I'm going to do is I will remove these images and I will recalibrate so that lower reproduction errors. So and the right side here, there are two different uh, figures here that are display like that is parametrics, pattern centric, and the camera centric. This is what exactly what we have done. So we'll go with the camera centric, and okay, now our reproduction error is less than 0.4, is somewhere around 3.55, 3.56. So the next step is to export these parameters. To export this one, I have two different options, whether to export this into the workspace, MATLAB workspace, or to generate a script. So let's export this as a into the workspace, and then we will generate the script also. So I will export, and when I export this, it is gonna ask me for the variable name. So by default, it has a name as camera param. So I'm not gonna change this one. And if we are interested to know the estimation errors, we will export this one. And if we have to do any processing again in the MATLAB, we can make use of this one. So let me just import. I will import, and let's visualize this in the like. Let's make sure we have these calibrated points in the workspace. So now I have two different variables in the workspace, that is camera params and also the reproduction errors. So let me just open this one, and let me see what's inside this. Okay, so now it has given all the uh, output from the calibration, that is image size, radial distortion. So since we two coefficients, since we had like lower radial distortion and zero tangential distortion. So and what I'm interested is like extrinsic and intrinsic parameters. Okay, here are my extrinsic and intrinsic parameters. So let me just open my intrinsic parameter. So now it's gonna, as I mentioned, like intrinsic parameter is a measure of uh, where you're measuring your focal length, uh, optical center, like say, so this is the focal length, principal points, and the image size. At the same time, it will give me the radial distortion and tangential distortion. In our case, tangential distortion is nothing but zero. So let me just close this one and go back to my calibration app, and I will try to export this as a MATLAB script. So now I have exported this as a MATLAB script, and let us see what exactly we have done. Let me just zoom this a bit. Okay, so initially what it has done, it has like we bought all the images into the app, and then we performed the detection to detect the checkerboards. So we detected the checkerboard, and after that, we what did we do? So we made use of those detected points, take the image points and the use points. So these are nothing but those detected points and the reprojected points, and made use of the function that is estimate camera parameters to estimate the camera parameters, that is intrinsic parameters. So it's going to give me the intrinsic matrix, extrinsic parameters, and the tangential and radial distortion. So now when we have our calibration parameters, we are good to go with so now we are done with the step 1. So we can proceed with the step 2, that is image rectification, and then disparity map, and then we will compute the point cloud. So it's better to go with the stereo camera. Okay, let's explore. Let us try the stereo camera app. Let me just close this one, and I will open this stereo camera app. So however, I have the camera parameters. I'm not gonna save the model, but let me just open my stereo camera calibrator, and let's see what is the workflow for stereo camera calibrator. It's gonna be the same, but the only difference is you need to add like 2 different images, that is from your left cam and right cam. So when I go like, okay, this is a stereo camera calibrator, it's almost like similar. So when I like try to import the images, I can only import the image from the like the stored one. So I will go like select the folder where I have stored my images. So here are my images, that is left cam and right cam. So I will select this folder, left cam, and then I will go, I will import those right side also. Again, so okay, right camera folder, I will select this folder and I will import. Okay, so now again it's gonna ask me to choose a pattern. In this case, we have 2 different options, that is checkerboard and asymmetric circle grid. So the images, what do we have is again the checkerboard images, and the size of the squares in the image are 30 mm. So we will enter the size of the squares, and we will import all these images into the stereo camera calibrator app, and then the calibration. So yes, it has 40 different images, 40 images, that is 20 from the right cam and 20 from the left cam. So now it has to detect all the checkerboards, and at the same time we will visualize how the rectified image is gonna be like processed, how the images will be after applying this uh, calibration parameter. The output of this computation will be used to design the 3D point cloud, where each 3D point cloud correspond to a pixel in one of the images. So as I mentioned before, like 3D point cloud, it's very heavily used in autonomous driver assistance system, that is ADAS system, also in robotics. Okay, so it's almost done. Okay, so it has accepted all the images and it has like rejected nothing. So now, okay, so as you can see, like it has detected in pairs, left and right, but captured with the different angles. So again, these green circles are my detected points, and this is gonna be my origin. And if you cross verify, the origin is gonna be at the same position for all the images. So now again in the like we need to uh, we can go with the coefficients, that are the radial distortion coefficient. If you have a higher distortion, you can go with the 3. And if you have a tangential distortion, that is a shift or an angle between the camera lens and the camera sensor, you can go with tangential distortion. So right now I don't have any, so I will go with the calibration. So now it's going to calibrate the images, all the pair of images, and it's going to give me the reproduction errors. Just inline this one. Okay. So now it has detected like those points and reprojected back into the image. At the same time, if you want to like see the rectified image, okay, so it has detected the points, and for us to visualize the rectified image, as we can see here, like these left and right images are aligned in a single line. It's like, yes, it has detected all the checkerboard and reprojected. These red points are the reprojected points, and the procedure, like the next step is gonna be the same, like to minimize the reprojection error is somewhere around 0.2, and further if I want to reduce this, I just need to drag this to the threshold or my accepted range, and it's gonna highlight the images that have a higher reprojection error. And let me just remove this and recalibrate all the images again to have the new parameters. So now I have okay, now it has recalibrated with the reprojection error less than 0.2. Okay, so at the right side, again, there are two different figures what we can explore. That is pattern centric and camera centric. So as I mentioned before, what is camera centric and what is pattern centric? So let's go with the camera centric. This is what exactly we have done. And yes, my reprojection error are like less than 0.2, somewhere around 0.15, 0.16. So what I'm gonna do is like I will export the parameters to the workspace, and I will proceed with the disparity map and 3D point cloud construction. So it's asking for the variable again and the estimation errors. So right now I'm not interested to look into this, like estimation error. So I will leave it as with the default name, and I will export this variables into my MATLAB workspace. So now I have stereo cam here, stereo parameters. When I open this one, so as you can see, like there are different parameters for camera 1 and camera 2. So when I open camera 1, it's gonna give me all the details that I need, that is image size, radial distortion, tangential distortion, intrinsic and extrinsic parameter, and focal length. So let me just close this one and start continue with my script, what I have here. So till now what we have done is we have completed step 1, and we will proceed with step 2, step 3, and step 4. So the next step is for image rectification. So currently I don't have a stereo camera pair. So what I'm gonna do is I will make use of my laptop cam itself to capture two different images. The first thing what I have to do is I need to load the calibrated parameters, that is intrinsic, extrinsic, and those distortion coefficients. So I already have my uh, in my workspace. So what I'm gonna do is I will proceed with step 2, that is image rectification. So since I don't have a stereo camera pair with me, what I'm gonna do is I will make use of my uh, webcam itself, and I will give a pause in between so that it can capture the left, like I can define as left images and right images with some modification. So we will explore this how we are gonna do. So the step 1 is to to set up the video input from the camera. So I have defined my device ID, started my video here like video input in a variable called vid. Okay, so let me just run this session, and we will see our variables in the workspace. So yes, let's proceed further. Okay, now I have all my video input and my video source. And the next step, what we are gonna do is we need to define the baseline. So baseline is nothing but it's a distance between the stereo camera pair. Since I'm using my webcam, it's almost negligible. So I will define a baseline as okay, we'll define as 0.1, 0.1. Okay, so I have defined my baseline, and then I can go with the next step is I need to make some modification or some adjustment so that from the left cam and the right cam. So what I'm gonna do is I will make use of the brightness, and I will adjust the brightness for left and right cam. So for that I need to get the initial brightness. So I will create a variable called initial brightness, and I will pass this. Okay, so I have stored my the brightness in my as my initial brightness, and then we'll start with an infinite loop that is till our camera is on, or unless and until we uh, stop the simulation, the disparity map, and also the depth 3D point cloud. So what we can do is okay, we will go with the infinite loop, and then we need to capture the images from the video. So adjust the brightness level for the first image and start the video of camera for the first cam. Okay, so let us adjust the brightness first. That is here it is. So I will copy and paste it here, and I will adjust the brightness. That is, I have defined the initial brightness, and I'm gonna, let's say for the right, we will increase the brightness by 10, and we will start the video. So I have passed the video input to the vid variable, and now what I'm gonna do is I will create a new variable, and I will take the snapshot of this video. Of the video what I'm running here. Okay, so this is what I have done. And for the next one, to capture the next image, what I'm gonna do is I need to give a small pause in between because it's increasing the brightness by 10, and now it need to either we need to increase or decrease the brightness for us to make sure, like, okay, these are the left and right images, and with some difference. So what I will do is I will okay, we will decrease the brightness by 10, and the video is already on, so I don't have to do this one. And we will take the snaps again and store it as frame 2. So now I have two variables, that is frame 1 and frame 2, and we are taking the snap in frame 1. I have stored, like I have taken the snap with after increasing the brightness by 10, and in the frame 2 I have taken the snap of the video after decreasing the brightness by -10. That is, I have a difference of 20 here in the brightness level between the left and the right images. So uh, now we have our images here, like stored in frame 1 and frame 2. We need to normalize this. So we need to apply the normalization technique and also the edge detection. Uh, so let's convert these images into a grayscale first. So let's create a new variable. And we will store, like, we'll use a function called RGB to gray. And we'll pass these images or these frames, what we have captured as an input, so that it can convert into a gray frame. So similarly, we will create one more variable, and we will convert the second frame to a gray frame. Okay, so now I have converted my images to a gray frame. And the next step is to apply the edge detection technique. So there are different edge detection technique. We can go with like any one of them. So let's create one more variable and add images in the variable. So I have two images, and I will that is gray 1 and gray 2. So it's a defined function. It's saying that find edges into the grayscale images. So it needed grayscale images. This is the reason why we have converted our image into a grayscale. So we will pass the gray frame, and like say, okay, now it's gonna suggest me for the suggesting me for the method. So let's go with the canny for now, and I need to create a new one for gray frame 2, and I will rename this as its map 2. And this we need to calculate the disparity now. So now we have detected the grayscale, and we have the grayscale images, and we have detected the edge, and now we have the edge map. We can proceed with the calculating of disparity or disparity map from the edge map. So to do this, like initially we need to define the disparity range. So let's define the disparity range first. I will say I will call it as disparity range, and let's create a matrix that is like, okay, we will start from 0, and we'll go up to, let's say, 64. So now we have our disparity range, and we can create our disparity map. So I will create a new variable called disparity map, and I will use a disparity function. So I will use this function, and when I open the bracket, it's gonna suggest me like what I need to pass into this. It is image 1 and image 2. These gray scale images, and I will define the disparity range. Disparity range is nothing but the difference in the color, what it's gonna uh, display in the in the figure with respect to the distance. So yes, now we have created the disparity normalization technique. So we need to apply the normalization for edge map and the disparity map. So we need to create 3 new variables now. That is, let's create the like 3 new variables, and we will average these 3 variables to combine the normalization like variables here, and I'm gonna make use of the same variables for me to not to change the code again. So it's taking 3. I need to calculate the normalization for 3 different variable, that is edge map 1, edge map 2, and the disparity map. So what I'm going to do is like I will make use of mat to gray function. So what this function is saying, like convert matrix to a grayscale image. Okay, so I will, and then I'm gonna pass the edge map 1 and edge map 2 for all the, okay, I will pass edge map 2 and my depth disparity map. So I will pass all these 3 into the mat to gray function and store all these results in the in new variables. So now what I need to what I'm doing here is I'm combining this normalization, the normalization what I have applied from edge map and the disparity map, and I'm taking an average of all these 3. So now we have combined disparity map, creation of edge map and disparity map. So okay, so sorry, we have like normalized, we have created a combined normalization from the edge map and disparity map. And now we need to convert this disparity map into a depth map. So we need to create a depth map from the focal length of our camera. What do we have? So since we have exported the parameters, extracted the parameters of the camera, and we have stored this in the workspace, we can make use of those parameters to find the focal length of our camera. So I will create a variable called focal length, and what I will, okay, where I'm gonna find this focal length is I will open the stereo params, and I can see here that okay, so there are 2 different camera parameters, that is camera 1 and camera 2. Since we are using the same camera and we are so like just increasing the and decreasing the brightness and storing into different variables, So this here is my focal length. So I'm gonna make use of this focal length to calculate the depth map. Okay, so what I need to do is like, I need to get this one, or I just copied the path, and I will define it as like, I'm interested only in the first index, assuming the focal length, like focal length to be equal. Okay, so yeah, so we will assume the focal length to be equal. And in the next step, we will create a depth map. So depth map we will be calculating based on the baseline what we had defined initially, and the focal length. Okay, so what we will do is we will like, okay, we'll get the baseline and multiply this with the focal length we just calculated, and then we will pass all this, and we will divide this with a disparity map to, so we need to create a point cloud from the depth map using the camera parameter, and we need to create a mesh grid. So let's like first let's get the size of the depth map, and so that we can have the exact number of rows and columns what we have uh, in the with respect to the depth map. So we'll calculate the size and of the depth map, and yes, so now we have calculated the size of the depth map and store it in the variable rows and columns. And now we need to create a mesh grid. So we need to define two more variables for x and y, like number of columns and number of rows. So let us just create two more variable, and we will make use of mesh grid function. So now I have number of columns and number of rows. I need to define three axes, that is x, y, and z. So these axes will be based on, again, the focal length and the principal point. So what principal point is like, okay, we will have here again the principal point will open any one of the camera, and principal point, oh, here it is. So we will take this principal point, and what we will do here is let's create like three variables, x, y, and z, for three different coordinates. So I need to define this coordinates, building my 3D point cloud based on the disparity map and the depth map. So I will define this x, y, and z coordinate from the depth map itself. So I will take all the points from the depth map, and then I'm gonna multiply, like I will pass this, all the mesh grid points. Let's say the first variable is u, and I'm okay, let me just complete this. There's an error. Stereo camera parameters, and the first, we are just interested in the first one, assuming that it has equivalent. Okay, so yeah, we'll divide this with the focal length. Okay, so this is the x variable, and we will make use of the same with just second index as y, 2D. I'm so my z coordinate is 0. So I'm gonna do is I will take all the points from the depth map into the z coordinate. So now when we have created the point cloud, we can create the figures and to display the normalized edge map and the depth map. So we will display this too. So we need to display two different maps. So what we are gonna do is we'll make use of subplot. So we need to create we need to plot two different maps, but into one figure. So let's say one figure, two different map, and this is for the first one. Okay. So okay, here is my like the combined map, which combines the edge map and the disparity. So I will get this and I will display as an image with okay. So when I like say when I use this one, I am sure it's giving me some suggestions to use. Okay, okay, what's saying is take image as an input and map and yeah, we will do okay, so we have displayed as a combined normalization map, and we will do the same thing for the depth map. Sorry, edge map. Depth map we have done. We will create a subplot, and this is gonna be our second image. So now we will input the depth map as an. So yeah, we have plotted our combined map, that is the normalized combined map, and the depth map in a subplot. So the next one is to display the 3D point cloud and refresh all the images. So this is like exactly the function what our since our script is running in a while loop, we need to update the figure after each uh, completion of each loop. So we will use this one to update the figure with each iteration. And now we will create the 3D point cloud and display that. Okay, so let's create a point cloud. So it's an inbuilt function, like it's a MATLAB function again to for storing the 3D point cloud. So we'll use this one and pass all the like X, Y, and Z coordinates. I will take all the X, Y, and Z coordinate. Okay, so now I have a point cloud and I want to display this. To display this, what I'm gonna use is I will use PC show and I will pass this point cloud as an input to the PC show. So yes, I believe we are done. We are done with the script. So let me just execute, like run section by section. So we will start our video here. Define the baseline. We'll start with an infinite loop. Okay, we have an error, and this, what is the error? Initial brightness. Unable to resolve the name. Okay. So my error has been fixed, and we'll run the script. Let me just see the simulation. Okay, so now it has displayed my image. That is, this is my figure. What I'm expecting is, okay, so now it has displayed my image. That is, this is my figure. What I'm expecting is a disparity map, edge map, and along with the edge map, disparity map is along with the edge map and the 3D point cloud. So now it has to detect the edges. Okay, so it's able to detect the edges, and it's able to display the disparity map. So that's me and the disparity map, and it's able to take this disparity map and display it into the point cloud. So let me just stop this. Yeah, this is what I was exactly expecting from the output or the simulation. So now I have the output here. So this is all for the camera calibration and the workflow. So what we have done is like perform the calibration using the calibration app to estimate the parameters of intrinsic, extrinsic, focal length, and tangential distortion and less distortion coefficient, since the tangential distortion was 0 in our case. So we perform the calibration using the camera calibration app, and then we pre-process the images, or we perform the image rectification for edge detection and the normalization of the images by converting those images to a grayscale images. And then what we did is we made use of the edge map to create a disparity map. And from disparity map, we calculated the X, Y, and Z coordinates and the points, and we reprojected these points back into a 3D scene.